Imagine for a moment that you are holding two coins. You flip them. One is in New York, the other in Tokyo. They land on heads at the exact same instant. Always. Einstein called this spooky action at a distance. We call it quantum entanglement. But what if I told you that this spooky action isn't just magic? What if it's actually a secret tunnel through reality itself? In late 2022, a team of scientists using Google's Sycamore quantum computer announced something that sounded impossible. They didn't just calculate numbers, they claimed to have successfully simulated a traversable wormhole. Did they rip a hole in spacetime? No. But what they did might be even crazier. They used a computer chip to prove that black holes and quantum chips might just be the same thing. To understand this experiment, we first need to look at the beast that ran it, the Google Sycamore. This isn't the laptop you're watching this on. Traditional computers think in bits, zeros and ones. A light switch is either off or on, but Sycamore thinks in qubits. A qubit can be 0, 1, or both at the same time. This allows it to solve problems that would take a normal supercomputer 10,000 years to finish. But in this specific experiment, they didn't ask Sycamore to solve a math problem. They asked it to simulate a universe. A tiny, two-dimensional universe where gravity behaves very differently. Here is where the black holes come in. For 100 years, physics has had a divorce problem. General relativity, Einstein's theory of gravity and wormholes, and quantum mechanics, the theory of atoms and entanglement, hate each other. They don't work together. But in 2013, two legends of physics, Juan Maldacena and Leonard Susskind, proposed a truce. They called it ER equals EPR. It sounds complex, but it's beautifully simple. ER stands for Einstein-Rosen bridge, aka a wormhole, a shortcut through space. EPR stands for quantum entanglement, when two particles are linked instantly across space. The theory claims they are the same thing. Entanglement is the wormhole. The spooky connection between two particles is actually a tiny, microscopic wormhole connecting them. Google researchers, led by Maria Spirapoulou and her team, decided to test this. They created two groups of qubits inside the Sycamore processor. Let's call them Black Hole A and Black Hole B. They entangled these two groups, effectively creating a digital wormhole between them. Then, they fed a single piece of information, a signal, into Black Hole A. In a normal simulation, that signal would be lost in the chaos. But here is the magic trick. They hit the system with a pulse of negative energy. The information appeared instantly in Black Hole B. Unscrambled. Perfect. It had traversed the wormhole. They didn't send the signal through the wires, they teleported it using the rules of gravity inside a quantum chip. Now, before you pack your bags for the Andromeda Galaxy, we need a reality check. Did Google create a physical wormhole in their lab? No, think of it like a video game. If you play a flight simulator, you are using the real laws of aerodynamics to fly a plane. But you aren't actually flying, you are simulating the physics of flying. Google simulated the physics of a wormhole. They proved that the math of quantum mechanics can perfectly mimic the math of gravity. It's a holographic wormhole, but this is still a breakthrough. It confirms that we can study gravity, black holes, and the fabric of the universe without leaving Earth, just by using quantum computers. We are standing on the edge of a new era, an era where computer chips don't just calculate, they reveal the geometry of space-time. If ER really equals EPR, then every time particles entangle, they are stitching the universe together with tiny threads of wormholes. Google just plucked one of those threads. The question is, once we learn how to weave those threads, where or when will we go next? Thanks for watching. If you want to know more about the dark side of AI or the secrets of the cosmos, hit that subscribe button. I'll see you in the next one.